Hey y'all, we are Memphis Communiversity and we're back for another Calculus Done Wrong lesson where we run calculus before calculus wrongs us. And today what we're going to be doing is we are going to be doing a comprehensive review of shape of curves. So instead of learning something new, what we're going to do is we are going to review our past several videos. Those are sine charts, f increasing decreasing, f concave up or down including inflection points, f relative extrema meaning local max or min, and also f absolute max or min, the closed interval method. So what we're going to do at the beginning of this video is go over and review these rules. Then we're going to provide an easy function where we're going to do each of these 5 questions for that function. And then finally, at the second half of the video, what we're going to try to do is we're going to try to do some of the weirder shape of curves questions, like the second derivative test or the alternative way to do absolute max or min. Another way to say that is, I believe, the first derivative test for absolute extrema. And we might take some derivatives that require product rule and chain rule. So, again, nothing new. If you need to, what we would suggest is to watch our previous videos. The link of that, our playlist, our shape of curve playlist is in the description of this video. Where if you need to see something particular like concavity or local extrema, we would suggest you watching that video before this one, because we believe shape of curves isn't the hardest questions in the world. It's still a derivative question and not an integral question. If you know the rules very well, if you know how to draw sine charts very well, you should be good to go. Sine charts are very important, so watch that video if you need help with that. So let's get started again. Let's do some shape of curves. Shape of curves is such a big unit. It's probably one of the biggest units on the AP Calculus exam, also college calculus exams, maybe just behind derivatives and integrals themselves. So let's get going. So again, what we want to start off with is the rule themselves. So shape of curves. So shape of curves. So there's going to be 4 main rules that require sine charts. Not a great drawing there, so let me just erase this and let me try again. Then evenly space this out. So, first rule, most basic rule, where is f increasing? So again, you have to know your rules very well. Where is f increasing? Well, that's when f prime is positive. Where is f decreasing? That's when f prime is negative. Basically, you're going up if you have positive slope, you're going down if you have negative slope. Keep in mind that for all of these questions, I always set up my format of my answer with 3 things. I always have the question itself, I have my justification, which is the rule, and then I have my answer. So for example, it could be like f is increasing when f prime is positive on the interval 1 to 2 or something like that. And also when I do my rule, I'm always as specific as possible. I want to do the same things every single time. So I'm always going to have f prime in my rule. I'm never going to say like the slope is positive or the derivative is positive or it is positive or just positive. I'm going to always have f prime is positive. Then the rule that's as easy as this, or maybe even easier because you're doing the second derivative, is f concave up. So f is concave up when f double prime is positive. F is concave down. No, this is a W, by the way. This is a terrible W still. Let me try it again for the 3rd time, maybe the last time. So f is concave down, that's when f double prime is negative. So just a few things about concave up or down. So first off, there's 2 rules for concave up or down. There's this rule right here, f double prime is positive. There's also the rule that f is prime is increasing when f is concave up. F is concave up when f prime is increasing. But we're not going to talk about that rule because that rule is usually only done. The main reason why you would do that rule is when the f prime graph is already provided. That definitely does happen, but that's in a later video. So for now, whenever I can take multiple derivatives, if I can take derivatives, I'm going to take multiple of them. So right when I see concave up or down, and they just give me a function like sine of x or e to the x or x squared plus 3x minus 1 or something like that, I automatically take 2 derivatives, boom, boom, boom. Same thing with concave down. If I can take multiple derivatives, I just automatically take multiple derivatives. Keeping in mind that as you're taking derivatives, it's often good to simplify each derivative as you go to make that second derivative simpler, because we want our lives to be a little bit simpler if possible. So again, right when I see concave up or down, I take 2 derivatives and I draw the sine chart of the second derivative as opposed to the first derivative. Then another very common question is, of course, f has a local max. So f has a local max at a point, for example, A. That's where f prime goes from positive to negative. At x is equal to A. F has a local min is the reverse. F has a local min at x is equal to A. That's when f prime goes from negative to positive. And why is this the case? Well, F has a local max when you go from positive to negative. F prime goes from positive to negative. Basically, you're running uphill and then you're running downhill. Positive slope, then negative slope. And local min, you're running downhill and then uphill. A few things to keep in mind as well. First off, sometimes they use the word relative instead of local, but they're the same thing. So relative maximum is the same thing as local maximum. Also, the answer is 1 point. This is called the first derivative test. Hopefully in the video, in a later part of the video, we will talk about the second derivative test eventually, but mainly what you're going to be doing as much as possible is this first derivative test. The last thing to fill out this grid is going to be inflection point. So F has an inflection point. F has an inflection point. There is a rule where F prime goes from increasing to decreasing, or F prime goes from increasing to decreasing, or decreasing to increasing. But again, that rule is only when you're provided an F prime graph, and it's easy to find where F prime is increasing or decreasing. If I can take multiple derivatives, I will do that. So it's where F double prime changes signs. For both of these two things, it actually has to change the sign. So for example, if you go from positive to negative, that's a local max. F prime going from negative to positive, that's a local min. But if it doesn't change the signs, that's just considered a critical point, but not a local max or min. Because remember, critical point is where F prime equals 0 or doesn't exist. Same thing with inflection point. It actually has to change signs. So F double prime could go from positive to negative or negative to positive, but it can't go from positive to positive, for example. It can't bounce at the on the x-axis. It has to actually cross through the x-axis. So this is mainly it. This is the grid that my students know very well because these rules come up so often. A few things to keep in mind. The left-hand column, or the left side, what that is for questions where the intervals are answers. So for example, usually the answers are, where's F increasing on the interval from like 2 to 5 or something. So the answer will be 2 to 5, or like 3 to 6, or 0 to infinity, something like that. For this, guys, these two things, the answers will be points. The local max themselves, the local mins themselves, or the inflection points. Another thing is that, again, on the top half, right when you see the words increasing or decreasing, or local max or min, you're just taking one derivative. And then when you have concave up or down, or inflection points, you automatically go for 2 derivatives. And these are the main rules. There is a fifth guide, which is absolute max or min. It's a totally different process. So that's why I don't usually include it in the grid, but we shouldn't leave him out. We shouldn't bully him just because he's a little bit different. These are the Sine Chart questions. Let's talk about absolute max or min then. So absolute max or min is just its own process. So I'm going to erase this. So absolute max or min. So we can erase shapes and curves. Let's do absolute max or min. Abs max, abs min. So anytime you have abs max or min, it has to be on a closed interval so that we can use the closed interval method. So the first step I always do is called locate the function. I don't know why I wrote A, usually I just write 1. So it's just locate. So keep in mind that sometimes the given isn't the thing you're trying to find the max or min of. So for example, if they say here's position, but you want to find the absolute max or min of velocity, you would first have to take a derivative just to get to the locate thing. And the given is never the important function, it's always what you're taking the max or min of, which I call the locate function. A lot of times it is the given, but sometimes it's not. And I like to write it even if it is the given. So the second thing we're going to do, the second step, let's put circles, that's going to be critical points. So critical points is when you locate that function, you're going to take the derivative and you're going to set it equal to 0. You're going to solve. So that's just that. Third step is to form the table with x's. On the right column, you're going to have the locate function. Again, the locate function might not be the given function. You only care about the locate function. So that's going to be f of x, for example. Then for the critical points, what do you put in the table? Well, you're going to put your critical points and your endpoints, A and B, and your critical points. But keep in mind that you're only going to put the critical points that fit within the interval. So for example, if your endpoints are like 0 to 4 and your critical points are like -2 and 3, you're only going to do 0, 3, and 4 because -2 is not within 0 and 4. Another thing to keep in mind is that sometimes the critical points do involve where the derivative doesn't exist, meaning you have sharp points, but usually it is just 0. So again, the steps are locate the function, could be the given, could not be the given, just find it. Second step is take the derivative, set it equal to 0 mainly, maybe does not exist, but mostly 0. And then form this nice little table where A and B are on there, and also the critical points that fit within those endpoints. So that's absolute max or min. I call this the 3-step process. Hopefully at the end of this video, we will practice the alternative way to do absolute maximum. Another title that some people call that, I think, is the first derivative test for absolute extrema, which is pretty similar to the first derivative test for local extrema, but just slightly different. But anytime I have absolute maximum, especially when there's an interval, I like to focus on this guy. So let's erase this and let's actually do an example. So again, we're going to list out a function and we're going to do all 5 of these questions on this one function because it's not the worst function in the world. So I'm going to erase this. So what we're going to do is we're going to consider this function right here. Let's say f of x equals minus 3x cubed. No, sorry. Don't know what function I'm going to choose. Let's just do minus x cubed plus 12x minus 2. So this is going to be my function. And what we're going to do is we're going to try to answer all the questions. Because the questions require me to take derivatives and second derivatives, I'm going to just take them right now. Now I'm just going to draw their sine chart. But keep in mind that you don't have to do this for every single question. For example, if the question is just increasing, you don't need to find its second derivative. But I'm just going to have the derivatives just listed on the board here so that we can easily answer the questions. So in this case, let's go for the derivative first. So what is f prime? Well, I'm just going to take the derivative using the power rule, of course. It's going to be minus 3x squared plus 12 minus 0 because the derivative of minus 2 is 0. Then you factor everything out. A key point is that anytime you're drawing a sine chart, you need to factor it as much as possible. Some number times x plus or minus something, x plus or minus something, x plus or minus something. So in this case, we are going to take out this minus 3. And we're going to get x squared minus 4. So that looks like it's minus 3x minus 2x plus 2 if we factor it. And now we're ready to draw the sine chart. So again, watch our sine chart video. That's probably our most important video of this playlist because every single one of these questions require drawing a sine chart. But usually the sine charts are pretty easy, like it is in this case. This is a famous sine chart. It has 2 zeros, 2 and negative 2. It's also negative, so we're dealing with a negative parabola. So we're going to have this and this. It's going to cross at negative 2 and 2, and it's going to be a negative parabola. Remember, we don't actually care about what this shape looks like because we're doing a sine chart of f prime. We don't care about the graph of f prime. So all we care about is that it's negative in this interval, positive in this interval, and then negative in this interval. Then what we're going to do is we're going to do f double prime. Again, just to speed things up a little bit. So what's f double prime? Well, it's just the derivative of minus 3x squared. So it's going to be minus 6x. Again, using the power rule, taking the 2, dropping it to the front, letting the negative 3 and 2 mingle, and then subtracting 1 from the exponent. The derivative of 12 is, of course, 0. So then I'm going to draw the sine chart of this because I don't need a factor anymore. This crosses at 0, and this is even a more famous sine chart because this sine chart is just a line. There's only 2 types of lines in the world, positive slope lines or negative slope lines. And in this case, it's going to be a negative slope line because y is equal to mx plus b, where m is negative 6. So in this case, it will look like this. Again, I don't really care about the line itself. I only care that it's positive over here, negative over here. So let's do some questions now. So again, just taking derivatives, drawing the sine charts are the most important thing. If you know the rules, you've already done all the hard work. So in this case, we're going to do where is f increasing? Where is it decreasing? So there's probably be more English words, but it'd be like, where on what intervals is f increasing? So right when I see f is increasing or decreasing, what I would do is I would take its derivative, I would do all this stuff so I could draw a sine chart, and now I'm ready for the answer. So again, 3 things always when you're answering. F is increasing, that's the question. Just letting the reader know that if you've forgotten the question, I have not. I'm going to write the question in the answer. So f is increasing. Then I like to talk about the rule just to build my confidence up a little bit so that I just know the rule. So in this case, the rule is f is increasing when f prime is positive. And then I'll finally say the answer. So again, I'm not looking at where f prime is increasing. I'm looking at where f prime is positive. So based off the sine chart, where is f prime positive? Looks like it's between negative 2 and 2. Now, I'm going to do decreasing, which is the same exact thing, but reverse. So maybe not the same exact thing, but it's f is decreasing. Where's that? That rule is f prime is negative. I just know my rules very well. You want to know the rules as well as possible so that you don't have to think about them and you can just apply them. So f prime is negative. Where's that? Well, it's going to be from negative infinity to negative 2 because that's where it's negative. And it's also from 2 to infinity because that's where f prime is negative. So on negative infinity to negative 2 and 2 to infinity. So Hopefully you see that once you have the sine chart of f prime, these questions are very fast as long as you know the rules correctly. You just look at the sine chart, and as long as you know what you're looking for, boom, 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 that's the answer. Question, justification, answer. F is increasing, f prime is positive on this interval, negative on the other intervals. So let's do concave up or down, which is as easy, except you look at the second derivative. So I'm going to erase this. So let's do f is concave up or down. Concave down. We're going to see these two intervals. So again, right when you see concave up or down, you don't want to use the f prime increasing decreasing rule because that's when an f prime graph is provided. What you want to do is if you have a function just like this nice beautiful function, what you want to do is you just want to automatically take two derivatives. So if I solve this question, solve concave up or down, I would take its derivative, then I'd take its second derivative, and then draw the sine chart. Now we're ready for the answer actually. So where's f concave up? Well, f is concave up when f double prime is positive. That's the justification. And that's where this is f double prime is positive. So in this case, it looks like it's from negative infinity to 0. So on negative infinity to 0. Nothing too crazy. Just look at the sine chart. Just tell me where it's positive. Tell me where it's negative. What's the answer to this one? Well, f is concave up down when f double prime is negative. So that's going to be from 0 to infinity. Again, just take that second derivative, draw that nice sine chart, know the rule, boom, 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 the answer's there. Now let's do local max or min. So I'm going to erase this real quick. Your first instinct whenever you're doing local max or min is the first derivative test. Hopefully we will do a second derivative test example in this video, but for now we're just going to do local max or min with the first derivative test because it's pretty easy. So what you do is you're going to first do local max. So let's do local max. Again, let's try to boost our confidence. Let's try to write the justification before the answer. So f has a local max at x is equal to blank because what's the rule? Well, f has a local max when it goes from positive to negative, meaning the derivative. Perhaps the justification is even more important than the answer. If this were a free response question on the AP exam, if you have the correct justification and you have the wrong answer, you might get partial credit, which is always a good thing. So in this case, where does f have a local max? Well, it's where f prime goes from positive to negative. Keep in mind, again, we're not looking at this upside down parabola, we're just looking at the signs. So where does f prime go from positive to negative? It looks like it's x equals 2. So it's at x equals 2. Now let's do local min. F has a local min at x is equal to, again, I'm just going to write the justification first so that I have it on the board or have it on the paper. F prime goes from negative to positive. And where's that? Well, it looks like it's negative and then positive over here, so it's x equals negative 2. Again, if it bounced, it wouldn't be neither a local max or min, it would just be a critical point. But in this case, the local max is this one right here. The local min is this negative 2 because it goes negative to positive. Write the justification, look at your sine chart, just have a fun time. The last one is, of course, inflection point, but let's do that one. So let's erase this. F inflection point. Again, there's two rules for inflection point. One of them is f prime. F has an inflection point when f prime goes from increasing to decreasing or decreasing to increasing, but you use that when you have an f prime graph. We don't have any f prime graphs in this video, so I'm going to use the f double prime rule. F double prime changes signs. So f has an inflection point, or abbreviated inf point. Try to not be as lazy as me. At where is it? Well, just where does it change signs? Looks like it's at 0. It goes from positive to negative. And then we'll write the justification because f double prime changes signs there. Keep in mind, it doesn't matter if f double prime goes from positive to negative or negative to positive, it's still an inflection point. But if it bounced, it wouldn't be an inflection point. So for example, we have this sine chart right here where this were 1 randomly, this were 3, and it went like this. And then f double prime, this would be the sine chart of f double prime. In this picture, where would the inflection points be? Well, the inflection point would only be at 1, it wouldn't be at 3, because f double prime is positive on both sides of 3. It doesn't change signs. Well, it does change signs at 1. So again, if you have this picture right here, F double prime would change signs only at 1, so that's the inflection point. 3 would not be an inflection point. But again, these questions are really easy. As long as you know the sine chart, as long as you know the rules. Let's do the odd brother. Let's do absolute maximum min to not leave them out. So what we're going to do is we're going to do absolute maximum min now. You do need to have an interval for absolute maximum min. So let's have the interval from 0 to 3. So let's get going. What we're going to do is we're going to find the absolute maximum of this function. So we're going to do locate first, the 3 steps, locate critical points table. I like to write the locate even if it's the given because I feel like I'm going to plug in the numbers more accurately if I write it in my own handwriting. Another thing is that sometimes the locate doesn't match the given, so it's nice practice to always write the locate function, meaning the function you're taking the absolute maximum of. So in this case, the locate would be f of x equals negative x cubed plus 12x minus 2. Second step is the critical point step. So second step is going to be critical points. So what you do is you're going to take the derivative of the locate. If the locate doesn't match the given, you no longer care about the given, you only care about the locate. So in this case, it's going to be f prime of x minus 3x squared plus 12. We already did this before. We set it equal to 0. We can take out a negative 3. It ends up being x minus 2 times x plus 2 because it's negative 3 times x squared minus 4. And again, this gives you x is equal to negative 2 and 2. So then what you do is you form your nice little table, the most important part, perhaps the most annoying part, unfortunately. But for the right-hand column, you do put your locate. No matter what it is, it might not match the given, but you put your locate function, f of x. That's why we like to write the locate thing, because it's easier to plug in numbers and just take it and plug it in if it's on your own handwriting. Then you need to just consider what numbers to plug in. So you always include the endpoints, so 0 to 3. And then you include the critical points that fit within that interval. So in this case, it's just the number 2. So we're just going to put the number 2. We are not going to put negative 2 because negative 2 is not within our interval. Then what you do is you plug in these 3 numbers into this separately. The biggest one is the max, the smallest one is the min. So in this case, when you plug in 0, it looks like it's negative 2. Then when you plug in 2 here, no shame in doing math on the side. It's going to be 8 minus 8 plus 24, I believe, minus 2. I think that's going to be 14. Then we're going to plug in 3 into this function as well. So it's going to be minus 27 because 3 cubed is 27 plus 3 times 12 is 36 minus 2. This is going to be 9 minus 2, 36 minus 27, so this is going to be 7. Once you have the table, then you're ready for the answer. The biggest y value or the biggest function value is going to be your absolute max. The minimum y value is going to be absolute min. Keep in mind the difference between the x and the y. I like to just write both. So f has an abs max or absolute max of which value? 14, because that's the biggest one in the table. And that's the curve at x is equal to 2. That's the worst 2 I've ever drawn. So I'm going to try to redraw it. Then f has an abs min. I'm going to try to save some space of negative 2 at x is equal to 0. So that's how you do absolute maximum min, especially on the closed interval method. Locate your function. Could be the given, could not be. Just find it. Then take the derivative, set it equal to 0. Put the critical points that fit within the endpoints as well as the endpoints into this table where you're plugging in these values into the locate step. Biggest one is the max, smallest one is the min. Those are the 5 main shapes of curves question. Good job, team. We did increasing, decreasing, concave up or down, local max or min, the same thing as relative max or min, and also inflection points, and finally absolute max or min. So let's try to sort of cover some odds and ends. Let's do some harder questions. Maybe a few harder questions so that we can sort of wrap up shape of curves review. So we're no longer dealing with this easy function. Let's do a harder function. So I'm going to erase this. So the first one I'm going to do is sort of a known one, which is f of x is equal to e to the minus x times x plus 1. And what we're going to do is we're going to try to see where's f decreasing. So again, anytime you see the word decreasing, just take the derivative and try to draw a sine chart. So in this case, we're going to take the derivative. It's just a little bit more intimidating of a derivative. Keep in mind that we're still taking derivatives, so if we need to apply the power rule, which we already did, we'll employ the power rule. If we need the product rule, we'll do the product rule. If we need quotient, we'll do quotient, and of course, we won't forget chain rule. So in this case, it's going to be product rule. So we're going to keep the derivative, keep the same, the first one, e to the minus x take the derivative of x plus 1, but that's just times 1, so I'm not going to complain. And then we are going to take the derivative of e to the minus x, but keep in mind that it's e to the minus x times negative 1 because of the chain rule. Just don't miss those little chain rules. The derivative of the inside function minus x is minus 1. Finally, we're going to keep the same. Another thing is that you can't draw the sine chart unless you factor everything as much as possible, meaning it's x plus or minus something, x plus or minus something, x plus or minus something. So in this case, we got a little bit of algebra work before we're ready for the sine chart. So it's going to be e to the minus x. Let's factor this guy in. So it's going to be minus e to the minus x times x. Then e to the minus x negative 1 times 1. That's minus e to the minus x. So notice good things happen. These things cancel. So you're left with minus e to the minus x times x. And this thing is simplified as much as possible. So now we're ready for the sine chart. One thing to keep in mind is that don't get intimidated by this e. It's actually a nice thing because when you multiply by a positive thing you get a positive thing. If you take a negative thing and multiply by a positive thing, you still get a negative thing. So basically when you're multiplied by positive things, you don't affect the sine charts. You certainly affect the graphs of the function, but we don't care about graphs. We only care about sine charts. So e to any power, even if it's negative, is going to be a positive power, positive number. So in this case, if you don't know, e to the negative x looks like this. It's always above the x-axis. So we can just x it out basically before we draw a sine chart. So the sine chart is really easy. It's just the line minus x. So again, that's this crossing through because it's negative slope at 0. Again, you can ignore that e to the minus x. You can ignore 5. It's the same sine chart as something like negative 5x, because the 5 doesn't affect the sine chart, because again, we're only drawing sine charts. This is a sine chart of f prime. We focus on the positive or negative, so now we're ready for the answer. Where is f decreasing? We put the justification first. It's where f prime is negative, not f double prime. It's where f prime is negative, so that's from 0 to infinity, and we are done. So that's where f is decreasing. Hopefully you can see that's f prime. Not a hard question. The only thing hard about this question was, again, the derivative. But the derivative, as long as you're careful with the product rule, as long as you're careful with the chain rule, you should be good to go. So let's do another hard question. So I'm going to erase this. So just a tricky question. I'm going to do this function right here. Not x squared minus 3. Let's do something that's factorable. Let's do x squared minus 16. And what we're going to do is we're going to find the local maximum of this function. Again, another way to say this is relative maximum. So right when you see this, your first instinct is always to take the derivative, and we're taking derivatives carefully. So what's the derivative of ln of x squared minus 16? Well, it's ln of something, so the x squared minus 16 goes into a fraction. But then remember, of course, you need to multiply by the derivative of the inside function. What's the derivative of x squared minus 16? Well, that's just 2x. Then we're going to draw a sine chart, but in order to draw a sine chart, you need to factor it as much as possible. So I'm going to change this to 2x over x minus 4, x plus 4. So we're good to go. Then what you do is don't get intimidated by fractions. When you're drawing sine charts of fractions, it's just the same thing. You just count the zeros. You do n behavior just like normal, zero behavior just like normal. So let's try to do that right now. F prime. So plot all the zeros you see, 0, 4, negative 4, in order of how they go. So on a number line, so negative 4 is first. Then you count the number of zeros. So it looks like we have 3 zeros here because there's none of these zeros are to factors or powers other than 1. So it's just 1, 0, 2, 0, 3, 0. Then everything is positive. So it looks like we have a positive odd function that starts at the bottom, goes towards the top. That's the end behavior. And then for zero behavior, what you do is you come to each zero and you just look at the power. If it's odd, it goes through. If it's even, it bounces. So in this case, because everything is to the 1, it'll go through in all of them. Then we only care about negatives and positives. And we're ready for the question. So where does f have a local max? Well, we know the justification. That's where f prime goes from positive to negative. So that's at x equals 0. Positive to negative. But this is the tricky question because notice that we cannot plug in negative 4 and 4 into f prime or into our original f because then the function wouldn't exist there because ln doesn't exist at 0. You can't plug in 4 because you'll get ln of 0. Same thing with negative 4. So even if these look like local mins, it goes from negative to positive, we actually can't consider them as potential candidates for local max or min. So actually this question has no local mins, no local minimum, even if these look like local minima. Hard to spell. Because even if it looks like it goes from f prime negative to positive, you can't even plug these into the derivative, so there's no way that there's a max or a min at those points. So just be wary of that. They are important because they help you draw the sine chart, so you can't just ignore them. They help you draw the sine chart so you get the right sine chart shape. I don't know why I couldn't say that. Sine chart shape, and it goes through 0 like this, positive, negative at this point. But again, these two things, while looking like local min, are not local min because you cannot plug them into your original function. But 0 is a local max. It does go from positive to negative. So that's enough for first derivative test for local max or min. Let's try the second derivative test. So let's erase this. So the second derivative test is used very rarely, but sometimes you're forced to use it. So f of x equals, for example, x squared plus 8x plus 2. So what we're going to do is we're going to try to find the local max and the local min of this function right here. So even if the second derivative test is called the second derivative test, remember that it really should be called the first derivative test and the second derivative test. Basically what you're going to do is you're going to find the zeros of the first derivative and plug it into the second derivative. You do not find the zeros of the second derivative. Be careful. You only take the zeros of the first derivative, plug it into the zeros of the second derivative. Also remember that it's opposite what you might expect. The second derivative being positive means it's a local, min actually because it's concave up. And the second derivative being negative means it's a local max because it's concave down. So let's talk about it here. So again, the first thing to do on the second derivative test, we're going to try to find the local max or min using the second derivative test. So first thing to do is first take the first derivative, 2x plus 8, just again using the power rule, set it equal to 0 and solve. So in this case, x is equal to negative 4. We're going to need this guy and we're going to plug this guy into the second derivative. So the second derivative is f double prime, just the function 2. Again, the main thing my students do is that sometimes this is a function like x minus 2, and they'll just be like, oh, I'm going to plug in 2 because that's the 0 of the second derivative. But you do not do that. That's actually the inflection point. What you do is you take the 0 of the first derivative, plug it into the second derivative, as I'm about to do. So we're going to plug in negative 4 because f prime of negative 4 is equal to 0. So what we want to do is find f double prime of negative 4. How do you plug in this negative 4 into this crazy function right here? Well, if you plug in any number, you're just going to get the constant 2. So this is 2. Again, be wary that if it's positive, it's actually a min because it's concave up, min at a horizontal tangent line. This guarantees that it's a horizontal tangent line. This guarantees it's concave up. So in this case, we have a local min by the second derivative test. And that's that. So second derivative test, even if it's rare, it's also not that bad. Take the first derivative, find the zeros of the first derivative, plug it into the second derivative. If the second derivative is positive, that means it's a local min. If the second derivative is negative, it means it's a local max. So finally, what I want to do is I want to do the alternative way to do absolute max or min when you don't have a closed interval. So let's do that real quick. So let's say we have this function right here. We can just start with this function. So in this question, what we're going to do is we're going to find the absolute max or min of this function and justify that it's an absolute max or min. And to be more clear, we're going to find the absolute min of this function, not just the absolute max. So let's do abs min. So be wary that in this case, we don't have an interval, and this is a good sign when you do the alternative way or the first derivative test for absolute max or min when you don't have an interval, so you can't draw the table, because in the closed interval method, when you draw that table, A and B, the interval points, the endpoints of the interval are always in that table. So if you don't have a table, you can't use the table method. So this is what you do. It's the same thing as normal. First thing you do is you take the derivative, so f prime of x is equal to 2x plus 8. Then you draw the sine chart of this derivative. This sine chart again is going to go through -4 because that's what causes this to be 0. There's only two types of lines. So it's this line or that line. And then this is going to be my absolute min. So let's write -4 here. -4. And when you're doing this method, the sine chart has to be this easy. F prime either has to be negative to positive if it's a min, or positive to negative if it's a max. It can't be a parabola or anything like that when you do this question. So then you write this nice little fancy sentence. It's really similar to the local max sentence or the local min sentence, except you're just describing the sine chart perfectly. Basically, what you're going to say is that this sine chart does only two things. It's negative for x smaller than -4, and then it changes from that to being positive from x beyond -4, meaning that it's just negative, and then it's positive, the derivative. So that last thing, that bottom point, has to be the absolute min, because the derivative doesn't do anything else. So in this case, the justification or the sentence that I make my students memorize is f has an absolute min at the number, meaning at x is equal to -4. And this is my justification. Because I'm not going to say f prime goes from negative to positive. That's the justification for local min. I'm going to say because f prime is negative for this side of the sine chart, so that's for x smaller than -4, and then f prime is bigger than 0 for x bigger than -4. So that's going to be my answer. Where does f have an absolute min? That's going to be at this point -4. This is my justification sentence. If you actually wanted to find the value, what you would do is you plug in -4. I can do that right now. What is f of -4? What is this value actually? Well, it's going to be -4 squared. That's going to be 16 minus 32 plus 2. So I believe this is -14. But again, the thing I'm trying to stress is this alternative way. Sometimes it does come up, especially because you don't have an interval, so you can't do the table. Your first instinct would be the 3 steps: locate, critical points, then our table there. But if you can't have any endpoints, you can't draw the table. So what you do is instead, you take a derivative. The sine chart has to be this easy. It either has to go from negative to positive or positive to negative. If it's a max, then you write the sentence. F has an absolute min at x equals 4, because f prime goes negative for x smaller than -4, f prime is bigger for x bigger than -4. That's the sentence I make my students memorize, and it's not that hard. Again, you're just describing the sine chart using math terms. But that's it for our comprehensive review of shape of curves. Hopefully this was useful for you. We reviewed all the big questions: increasing, decreasing, concave up or down, relative maximum min, inflection points, and also absolute maximum min. Then we even talked about taking derivatives more carefully. We talked about the alternative way to do absolute maximum min. We talked about second derivative tests. We talked about weird questions and the relative maximum min with the ln's and things like that. So hopefully you should be good to go. Certainly though, this is a very important topic again. So if you want more practice, check out our video, our Girls Teach Calculus video, which is in the description of this video, where one of my former students does several of these examples. She practices maybe questions that are involved fractions, maybe some trig questions, some basic ones, all the big topics like increasing, decreasing, concave up or down, etc. I think she does one where she does an alternative maximum min question. So if you want more practice, go check out that video. Again, if this was hard for you or if you don't know the concepts very well, we do encourage you to watch our previous videos where we talked about each topic in depth. And if you know how to do this, if you know how to do the algebra, continue on with our shape of curves journey, where again, we're going to do those rules that we alluded to earlier, which is that f is concave up when f prime is increasing when we have these f prime graphs. So instead of taking derivatives and drawing our own sine charts, what's going to happen is there's going to be a nice, beautiful picture of f prime already, and then we're going to do our shape of curves rules on f with that graph of f prime. But until then, thanks again for watching, just like normal, and I hope to see you next time.